Okay, good afternoon. It's a second lecture on the phonons. Last time I introduced phonon as a concept and the way to look at this phonon by neutrons. But phonons were supposed to be a sort of general concept, I did not get into details, particularly for complex structure. But I pointed out, for instance, the effect of harmonicity, electron-phonon coupling, and how phonons are affected by the structure, etc. And then at the end, we went into a little bit more complex system of ionic solid, ionic crystals, which has plus and minus ions. So in this case, plus ion and minus ions move in different way. As a result, the phonon branch splits into two. One is called acoustic mode, the other one called optical mode, because optical modes are optically active. It, for instance, absorbs infrared if the symmetry is right. So optical phonons are very interesting in that sense because it controls the dielectric properties of the solid. So for instance, if phonons are frozen, so that such a way that the plus and minus ions are displaced permanently, then you have ferroelectricity. So and this happens by the softening of this transverse optical phonon. Because, as I explained, because of this Lyddane Sachs-Teller relationship, the frequency of LO and the frequency of TO are related to low frequency and high frequency dielectric constant. So in ferroelectrics, because of the strong permanent polarization, the low frequency dielectric constant is extremely high. That means epsilon 0 or epsilon infinite ratio is quite high. So omega LO to omega TO ratio becomes quite high. And omega LO cannot be that high. It's limited by spring constant and weight. So what happens is that frequency of TO becomes very small. And as a result, this ratio blows up. That means near the transition temperature, the frequency of TO goes down to almost zero. And that is the soft mode, which induces ferroelectricity. Of course, in reality, TO phonon never goes to zero. But anyway, that's details. But the idea is that the softening of the transverse optical phonon induces ferroelectricity. Now today, I'll get into even more complex situations in which the unit cell has many atoms in it. Now many people are studying a complex compound, such as oxide and chalcogenase and these compounds. Therefore, you always have more than one atom in the unit cell. So the position of atom is defined not only by the unit cell. Ri refers to the position of the unit cell, but the position of inequivalent atoms. For instance, if a unit cell has 5 atoms, there are 5 distinct positions. So alpha goes over this non-equivalent number of atoms within the unit cell, and then displacement of that particular atom. So this particular atom belongs to the ith unit cell, and alpha refers to the number of atoms within the unit cell. So again, I goes 1 to infinity, but alpha goes to 1 to the number of atoms in the unit cell. So it's the same equation, but it becomes a bit more complex because of addition of this term that specifies the position of each atom within the unit cell. But our alpha and our beta are independent of the unit cell. It's the same for each unit cell, right? So you can take this out of this summation. So what happens is that this is the regular lattice sum term, and then comes this unit cell modulation term, and then the theta expansion that we discussed 2 days ago. Okay? So the phonon coordinate carries also not just the position of the unit cell, but also position of this non-equivalent atoms. So there's a prefactor. This is due to this each non-equivalent atoms. For instance, R could be 0 if an atom is at the corner of this unit cell, or half and half and half if it is the center of the unit cell. So this factor changes the so-called this factor becomes a structure factor of this particular phonon. So this changes the amplitude of the phonons, and therefore not all phonons look alike. Different phonon branches depend on Q in different way because of this factor. And this factor can be easily calculated, so we can it is not that difficult to understand why certain phonons behave that way. So let me show you an example. For instance, this phonon, right? This phonon is pretty strong here, but weak here, right? It's strong around H equal 3, but very weak around H equal 2, or you almost see nothing, or H equal 4. Yeah? You almost see nothing. On the other hand, this one is strong around H equal 2, but weak around 3, and strong again around 4. So this particular mode is strong when the H is even, and this one is strong when H is odd. And that, if you calculate this factor, immediately tells us that this atom is on the corner of the unit cell, and this is at the center. And actually, this is the phonon spectrum of YBCO superconductors. So these are due to copper ions, and these are due to oxygen motion. So highest frequency modes are almost entirely due to oxygen motion. That is obvious because oxygens are lighter. And heavy atoms like barium has a lower frequency. So anyway, the point is that this modulation of the intensity reflects the structure within the unit cell and complexity because of the makeup of the unit cell. And if you have n number of atoms within the unit cell, then you have 3n phonon branches, always 2 transverse and 1 longitudinal modes. And when in the complex structure, the only 3 of them are the acoustic phonons, while all of them are all others are optical phonons in some ways. So you have a very, very complex structure. And as I show you, this is the earlier case. The intensity of these phonons change with the parameter HKL indices because of the structure factor. So if you prepare this beforehand by simply placing the intensity, you can identify what kind of phonons you have. So as you can see, that phonon intensities are not the same. Some of them are strong, some of them are weak. Part of that reflects because of the difference in B, but this reflects mostly the difference in the structure factor. So let's make it even more complex. In a case where the unit cell has infinite number of atoms, that is the case of glass and liquids. So in this case, there's no unit cell. Unit cell is the sample itself. However, because atomic distances are not random, not arbitrary, okay? It's random, but not arbitrary. For instance, two atoms cannot come too close to each other, right? There are certain distances that the atoms cannot come closer. So as a result, there's some kind of short-range order. So what happens is that if you take a diffraction pattern, instead of black peaks, you have a broad diffuse peak like that. So this is the diffraction S of Q from liquid helium. So here, this corresponds to the first black peak. So that represents kind of interatomic distances. And instead of black peak, we have a broad peak. So if you have a black peak, this phonon, as I explained last time, comes down to 0 because 1.0 is physically the same as 0, 0. These are gamma point. So physically they are the same. Therefore, phonon frequency comes down to 0. That is if you have black peak. But here you don't have a black peak, and you have a diffuse peak. So the phonon frequency does not come down to 0 at one point, but it comes down to over range of Q. Everything is diffuse. All right. So as a result, you don't see this clear umkrap. Altogether, it looks like it's not a sharp line, okay, broad line, diffuse line, but it looks like it comes down and then up again. Right? So that's what happens all the time, and that is called roton behavior. That represents this diffuse umkrap. Oops. Yeah. So that's the typical dispersion, phonon dispersion in glasses. It's a silicate glass, and that's the transverse acoustic phonon become localized, longitudinal phonon, acoustic phonon that goes like that. Okay, and with each one of them, it's shown by a single ball point, but actually it's just a peak position. Phonon is very, very broad, like that. This is another example in the glass. As you can see, that at the low frequency, phonons are pretty sharp because low frequency phonons are long wave phonons. So if a wavelength is long enough, then the structure doesn't matter. Atomic structure doesn't matter. It behaves, the whole thing behaves like a solid. So detailed atomic structures are not that important. So the phonons are more damped than in crystals, but still it's well defined. But if you go to high frequency, they become very, very broad, like that, right? Very broad. So low frequency phonons are propagating, but high frequency phonons are localized. This is a dispersion of liquid helium. Again, as I said, it goes up, but then come down by umkrap, diffuse umkrap, and then go up again. And that's the so-called rotons. And Lev Landau explains the behavior of liquid helium in terms of this roton behavior. And this data show intensity profile. That this is at each particular Q, this is a Q at 1.13, so it's around here. It's around here. How the peak shape changes with temperature. So in regular normal fluid, this peak is very broad, right? But it becomes sharp when the helium goes into the superfluid state. In the same way that this peak, which corresponds to the roton, that's the roton frequency. This is a little bit sharper than this peak, but it becomes really sharp below at low temperatures when the system goes into a superfluid state. So if you plot frequency of this particular mode, this is a roton mode. Frequency increases when the system goes into superfluid, but at the same time the width becomes very, very sharp, right? Because the system is a superfluid, so atoms do not interact with each other. It's in a condensed boson state. So this phonon scattering becomes less and less. Yeah, the one that we discussed last time. The dissipation due to this phonon-phonon interaction becomes much less. So this is very much like phonon becoming sharp in the superconducting state because of the absence of electron-phonon coupling within the gap. Okay. So the roton as a function of temperature looks like this. At high temperature, it's all broad and become very sharp at the low temperatures below the superfluidity transition temperature, so-called lambda point. Now, let's turn into a slightly different subject, that is the phonons in real space. Because so far we have been discussing phonons in K-space. You know that phonons are like plane waves. It has a specific wave vector and propagates in solid or liquid like a plane waves. Now in disordered system, however, the phonons are very strongly scattered, and some phonons become localized, as I shown you for the liquid. So it is useful to think how the phonons would look like in real space. And this is important because when we use pair density function method, PDF, everything is turned into to real space. So we have to know what is the behavior of phonons in PDF phenomena. So first thing that I'd like to point out is so-called Placzek correction, and this is a standard procedure used in the PDF package. If you use a PDF package, there's a choice of Placzek correction. And to make the long story short, I recommend against using Placzek correction because it does correct something, but actually the damage is larger. So I'll discuss why it doesn't work. So I introduced this equation before, okay? If you have a S of Q, SQ minus 1 Fourier transform, sine Fourier transform gives you the pair density function. That's a distribution of interatomic distances. And in that, we assume for elastic case, Q0 is equal to 2k sine theta. Yeah? This triangle of Ki and Kf will give you Q is equal to 2k sine theta if Ki is equal to Kf. So this is perfectly okay for elastic case. But for inelastic case, Ki is not equal to Kf. So in this case, this equation doesn't work, right? And the Q is related to Ki and Kf in a rather complex way. And the difference between Ki square and Kf square gives you the energy transfer. Q is the momentum transfer, and omega, h omega is the energy transfer. But in regular powder diffraction, we do not measure Ki and Kf separately. Okay? Only in inelastic measurement we separate them. But in powder, you just measure the total time of flight. For instance, in case of pulse neutron scattering, you assume Ki to be the same as Kf. So you assign, just like elastic case, Q to be 2k sine theta, which is not right. So this mistake induces some need of a correction. So by using this equation, we can further expand Q square, which is like that, and then if you expand that, you get this equation. And from that, you can determine Q in expansion in terms of omega. So as you can clearly see, that if omega is 0, that is elastic. So this term is gone. So Q is equal to 2k sine theta. Right? But in case of the inelastic one, omega is not equal to 0. So there's a correction here. So in the Placzek correction, you assume a ballistic interaction. That is that the neutron hits an atom one to one. You know, you don't sort of transfer momentum to the crystal altogether, but you just hit one atom randomly. So in this case, the total energy transfer becomes the kinetic energy of one atom. Here, m is the mass of an atom. Okay, so that's the kinetic energy of an atom. So by using this, we can expand this. You know that this term is the shifting Q, you know, out of this Q0. So this term is equal to mass ratio. This n is a neutron mass, and m is an atomic mass times sine theta, etc. Right? So this ratio is small, so it's not a big effect, but still it is a significant effect, particularly for light atoms, and also if theta is large. So this PDF package usually has this correction due to this shift. But if you do that, this is what you get. That's the observed S of Q. And if you use the Placzek correction, you get that, but the bottom drops down at low Q, which is obviously wrong. So if you use Placzek correction and then calculate PDF, you get a crazy result because of this low frequency, low energy correction. Oh, I'm sorry, this is not R, this is Q. So Placzek correction overcorrects at low Q. This is a QA minus 1. And this is because at low Q, as we discussed in case of multiple multi-phonon processes, at low Q, the elastic process is dominant, so you don't need a Placzek correction. So we are working on the better process than procedure than this Placzek correction. Now, let me go even to a sort of newer concept of dynamic PDF. PDF so far has been the static, the quantity which reflects the structure. But actually, you can include dynamic motion of atoms in PDF too. So as we saw, the experiment, a neutron scattering experiment, gives you SQ omega, which is like that. Dynamic PDF is a Fourier transform of this SQ omega from Q to R. So it is made of these delta functions, but it's moving with time. So therefore, it depends on frequency. Okay. So if you just take omega equals 0, that's elastic one, right? If you take a purely elastic one, this is omega equals 0, this is 1. So you get average of this quantity. That is called static PDF, right? But nobody looks at this. But many people look at the instantaneous PDF, that is the PDF integrated over energy. So this SQ omega is integrated over energy in case of elastic measurement or powder measurement. Powder measurement does not have this analyzer after the sample. So the X-ray scattering is this type. In X-ray scattering, regular X-ray scattering, energy resolution of X-ray is like 1 eV, and phonon energy is again tens of millivolt, right? So in X-ray scattering, you just measure everything. You integrate every phonon, and then you get, if the integration is made, then this becomes delta function, so over t. So what happens that we are looking at the same time correlation function, okay? Because of this atom and the other atom at the same time. That's why it is called snapshot, instantaneous snapshot. So X-ray scattering is a snapshot. People say that X-ray scattering is a snapshot because the X-ray energy is high. Well, that is not quite true. Simply because energy resolution of X-ray is lousy, so you get a snapshot. You can get SQ omega if you use very high resolution, and you can get elastic SQ or inelastic. But anyway, so that's the X-ray type. So this is an example of difference between elastic PDF and instantaneous PDF. Okay, elastic one averages out over the phonon motion. Inelastic one freezes phonon at each instant. The atoms are frozen and calculated. So inelastic instantaneous PDF is narrower, sharper than the elastic PDF. So the difference between them, these two are due to phonons. So the next step is to understand how this difference depends on the frequency. Okay, so that is the dynamic PDF. So a long time ago, this is 54, Van Hoff already pointed out that this dynamic structure SQ omega is related to the function which is called Van Hoff function. That is the correlation function as a function of R and T, position and time. So it's an exact relationship. Essentially, that the Fourier transform over Q and omega gives you the function which is in real space and time. So you get distribution function, atomic distribution function as a function of distance and time. Well, this is known for a long time, but almost nobody uses this function. I only know one case where experimentally this was determined, because it is not a useful function. Instead, this function in which omega is Fourier transformed into t, SQT is called intermediate function, is quite often used. So SQT is this quantity, okay? It's an e to RQ, but difference in time. And this from SQT to this, the intermediate function, then if you Fourier transform from Q to R, then you get Van Hoff function, okay? So these three are known. But nobody used this route in which you keep energy as energy, but you Fourier transform from Q to R. And this is the dynamic PDF. And then from here, if you Fourier transform from energy or omega to time, then you recover a Van Hoff function. Okay, so you can go from the dynamic structure factor to Van Hoff function in two ways, either through QT, intermediate function, or through a dynamic PDF. So this is an example of an intermediate function. This is the when you look at some glass or liquid. This is a case of a liquid, but intermediate function is rather strong function of time and decays like that. And you can see that in this particular case there are two steps. And this gave us a very useful information about the dynamics of liquid. So this intermediate function, this time scale is called alpha-relaxation time, is often used. But not dynamic PDF. Dynamic PDF is the other way around. It's not QT, but it's R omega. So that function is like that. So the idea is that if you do, for instance, a pulse chopper experiment, then you can get SQ omega at once. So this technique became feasible only recently. Right? Before this, the time of flight, this spallation source became available. If you have only triple axis, then we can do inelastic scattering only at one Q. Okay, you fix Q and do energy scan, right? So in order to get this two-dimensional data, you have to do many scans. Okay, many energy scans at different values of Q, and that just takes too much time. So nobody did this kind of experiment. But today, because of this spallation source, we can get this two-dimensional data right away. So triple axis experiment was very slow. You just scan at one energy and you get one peak at a time and analyze the peak. But this spallation source experiment is it's crazy. It's a parallel measurement, so you get SQ omega at once. So in elastic time of flight measurement, you get data of maybe a few thousand byte, but in the time of flight experiment, you get gigabyte or even more. A huge amount of data. Okay, so this is the power of the modern analysis technique. So this availability of this spallation source and time of flight chopper machine changed this game completely. Because as I said, that we can get SQ omega in two-dimensional pattern completely altogether. So the old way of analyzing this SQ omega is to look at this, for instance, phonon dispersion like that. Okay, that was the old way of analyzing this. But this dynamic PDF does not look at this the QE space, but simply Fourier transform from Q to R. So this is the diffraction, the SQE dynamic structure factor of polycrystalline nickel, and from this it's hard to make any sense. You have a sort of blur, but it's not easy to analyze what is going on. But if you Fourier transform, surprisingly you get this. Here, this peak is due to the first nearest neighbor. We are looking at nickel, FCC nickel, at room temperature. So 2.5 angstrom is the distance of nearest neighbor. And then the second nearest neighbor is this guy, and then third nearest neighbor is this guy. So as you can see that the low frequency phonons are just represented by peak. But high frequency phonons is split. Okay? And this is because at this frequency, there's so-called Van Hoff singularity. The phonon frequency becomes, phonon dispersion becomes flat. So I'll not get into details, but here phonons become localized. Okay? These phonons are localized. So DPDF picks up only the localized phonons. You know, propagating phonons are not really seen. So if you wanted to study propagating phonons, the regular SQ omega analysis is better because it gives you dispersion, right? But if you wanted to study localized phonons, then this technique is better. So in perfectly crystalline materials, you don't need this. But in highly disordered system, either crystalline or liquid and gases, this DPDF is very useful. And this is the case of lattice phonons, but it's useful for spins too. So this technique gives you the state of localized spin fluctuation. So we are planning to do such an experiment. So as an example, I'll give you a case of a very complex ferroelectric, so-called relaxer ferroelectric. So relaxer ferroelectric is a disordered ferroelectric. I discussed this also briefly when we discussed the structure determination by PDF method. The regular ferroelectric solid like barium titanate shows very strong coupling between the electric field and force. That's why they are used in a microphone and speakers and stuff like that, to convert electric signal into vibration. It is also used in STM and to change electric field to a displacement. Now this piezoelectric signal, however, is very sensitive to temperature in case of regular ferroelectric, because this coupling happens very strongly only near the critical temperature. And if you're a little bit away from critical temperature, you don't get much. So that's rather inconvenient because you cannot change the temperature of the device. So the real ferroelectric device used everywhere are not pure barium titanate and lead titanate and these things. Much more complex mixed system, often particularly so-called PZT, lead titanate. Zirconium titanate, PZT. And PMN is even more disordered system. It is so disordered that the phase transition is unclear. It's like a glass. It's glassy. So the power electric gradually become ferroelectric. But during this gradual transition, it shows a very, very high response. So relaxer ferroelectric are excellent material for application. But it's a mess. And here, for instance, this corner position is occupied by niobium, which is 5+, and magnesium, which is 2+. Okay, randomly. There's some order, but it's not important. Randomly occupied. So the structure is extremely disordered because the niobium 5+ and magnesium 2+ would be very different. The oxygen position around them are very different. So, you have to understand this behavior. For instance, if you look at phonons, you can observe phonons. These are the phonons by neutron scattering. And as you can see, compared to the crystalline case, regular crystalline case, phonons are very broad, right? Very broad. In crystalline materials, it's much sharper, but this is very broad. And this is because of this strong disorder. Strong disorder. Not only that, below a certain wave number, it just disappears. Phonon disappears, okay? This phonon usually should be like that, but it simply disappears. It may or may not go down, so it's sometimes called a waterfall. But essentially, that this phonon disappears. And this is because phonons become localized. Okay? If a phonons are propagating, then it shows up in regular SQ omega measurement, because wave vector is well defined. Okay? But if it is a phonons are localized, there's no specific Q. There's no wave vector. Okay? You know that you can make a wave packet by summing up all this wave numbers, right? So localized phonon represents wide distribution of wave number k. So you just cannot see it by this regular SQ omega measurement, and yet this formation of such a local state is considered to be important in understanding this relaxer ferroelectric behavior. And more than that, this is the sort of the ferroelectric polarization. Ferroelectric polarization sort of gradually disappears around room temperature, around 0 degree centigrade rather. And in case of barium titanate, nothing happens above. But actually, you see lots of very strong response, even room temperature and above, even though there's no polarization. The permeability, so-called electric permeability, is high, and optical response shows the presence of ferroelectric polarization up to very high temperature, like 600 K or 300 centigrade. So something is happening from usual QE temperature up to this temperature now called Burns temperature, because Burns was the first to, Burns and Dacol was the first to discover phenomena. So, and this is the range actually useful in the real application. When you have the ferroelectric polarization, the sort of a coercive field, in other words, that the field to move polarization becomes a bit too high. So you need a big field to move polarization. But here, you don't have a polarization, but you have a very big response. So as a result, a very small field, small electric field can change things very much. So that's why this material is very useful. So we did this SQ omega measurement, and took a Fourier transform of this SQ omega into dynamic PDF. Okay, so again the plot is energy versus distance, because from SQ omega we kept energy scale, but change from Q to R. So what happens is that this phonon is sort of again regular phonon up to 10, but here you see a split, okay, local phonons. And this guy also splits into this. This one also, for instance, splits into 2, right? So you can see local phonons at high frequencies, but not at low frequencies. So the behavior at high frequency is different from low frequency. And this temperature, 450, is the temperature around here, okay? So well above this room temperature, but below the Burns temperature. So this is a range where you see no ferroelectric polarization, but you see a lot of ferroelectric response. So we looked at this PDF at different temperatures. Okay, this is at 450, but we looked at different temperatures, but made a cut at the different frequencies. Okay, so the first cut is made here at the low energy, low frequencies, so it's nearly static case. So if you look at that, you do see this side branch, okay, splitting, and that is because of this ferroelectric polarization. So you see polarization in the static frequencies, and this persists up to maybe 250 or 300 or something like that, right? 250 or so. Okay. So this corresponds to this polarization. Static polarization persists up to 300 or so. So that shows up at the low frequency. So at this frequency, at this temperature, for instance, this is above the QE temperature. So there is no split. There's no polarization. But at low temperature, the polarization shows up. Okay, these are polarizations. So, and then disappears around room temperature. But if you go to high frequency, this is the 10 to 20 millivolt, okay, which is this range, okay, this intermediate range of frequency. This is low frequency. This is high frequency. Then you see this side branch due to polarization, okay, all the way up to 600. This one, persists up to 600, and then only here they merge into one, right? It splits like that into two. So this shows you this. There's a dynamic polarization up to 600 Kelvin. Okay, so this again corresponds to this temperature. So up to this temperature, some kind of response is there, and then optical response is there. Something is happening even though there's no real ferroelectricity, and that is because there are local dynamic polarization. The static polarization disappears at room temperature and nothing above, but dynamic polarization persists up to temperature as high as 600 Kelvin. So this same technique can be used for the study of a liquid. So this moment is just a simulation. We are now still doing calculation, measurement rather. But if you calculate this dynamic PDF in the liquid state, you can see that at low frequencies you see regular some short range order, some structure. This corresponds to the nearest neighbor, second nearest neighbor, and the third nearest neighbor. So you see some structure beyond the nearest neighbor. But at high frequency beyond 10, there's nothing here. There's nothing here. The average frequency of this system is about 40 millivolt. So derived frequency is about 40 millivolts. So over a very wide range of frequencies, there's nothing here. That means only the nearest neighbor is involved in the vibration. Can I go to? As I said last time, the phonon frequency is determined by this so-called dynamic matrix, which is this square of E, the alpha, the beta, alpha beta. That's a matrix. Alpha and R beta are like x, y, z Cartesian coordinates. So this is the 3 by 3 matrix, 1, 1, 1, 2, 1, 3, etc. So if you have a simple system, then simply diagonalizing this matrix, then you determine frequency. So you get a bunch of frequencies right away. For instance, if you have a very simple system, okay, like a cubic, simple cubic system, then this is only connected to that guy, and that only connected to that guy. Okay, there's no XY connection, so you only have this the diagonal term, so it's easy. Right away, you can diagonalize it. But in a three-dimensional system, you have to diagonalize this dynamical matrix. But in liquid, the atoms are moving all the time. Okay? So this dynamical matrix actually is time dependent. It changes with time. So diagonalization makes sense when you have diagonalization from D to by unitary transformation. You see, you usually D to this kind of transformation to D prime, and you diagonalize it. You get equation of motion because you assume that the M F is equal to MA, and this this is x2 dot is made of eigenstate. That the stationary state with a fixed frequency, such as this regular I, K, R minus omega t, with a fixed frequency. Therefore, the diagonalization gives you the eigenstate, which does not change. Okay, this state itself does not change. Amplitude changes, but the state does not change. You stay on always with particular K. Only when you have interaction with the, for instance, harmonic stereo cell, you have the phonon scattering, and lifetime is limited, but still, eigenstate will give you approximately the eigenstate of the system, the phonons with the quasi-particle. Elementary excitation, but not in liquid, because dynamic matrix changes with time. So by the time that atoms go here, the neighbor goes away somewhere already. Okay. So there's no harmonic oscillation. if neighbors are fixed, then this guy can go back and forth and oscillate. But in liquid, if this guy goes, the neighbor goes away. So there's no this regular oscillation. In spite of that, if you measure specific heat, then it goes up like that, and then jumps at a temperature called glass transition, but it comes back again, and then satisfy this so-called Dulong-Petit law, which is that the CV is equal to 3K. So this was a long time sort of a mystery why this Dulong-Petit law is observed even though there is no phonon. And this localization gave the answer. The phonons are completely localized, and there's a different mode existing at high temperature liquid. So I just explained both the phonons in K-space, that is for the static phonons in periodic crystal, and real space, that's in liquid, and ferroelectric, relaxer ferroelectric, essentially like a liquid-like behavior of electric polarization. And glass is in between, so you have to use both methods to look at the different behavior. Also that the strongly disordered system are in between too. So both K-space method and R-space method are useful. So neutron gives you both. So so far the people have looked at this the phonons only in K-space or Q-space. But I think more and more that this real space approach becomes viable as people look at more complex materials. Okay, so this ends up this phonon discussion of neutron scattering. Thank you.